A big focus of what we're learning in section 4.6 is involving position, velocity, and acceleration problems. So often we will abbreviate that SVA for position, velocity, and acceleration. But in order to do that, we need to understand something about piecewise defined functions and absolute value integrals. So when we're integrating a piecewise defined function, let's consider this one. We have f of x is 1 minus x for values of x less than or equal to 0, and x plus 3 for values greater than 0. And we want to integrate that from -3 to 4. So we know graphically that would be like finding the area between the curve and the x-axis, even though this isn't really a curve, from -3 all the way to where x equals 4. And so if we were to do this like without, we could do this with just the graph without actually integrating, since we have this graph and we essentially have two trapezoids. So like my first trapezoid, I know my area is the average of the bases. So my bases are 3 and 1. I multiply that by my height, and then I divide that by 2. So we should get an area here. I think I said 3 and 1. Sorry, my bases are 4 and 1. So I should get an area here of 7.5. And if I integrate and I consider this trapezoid, if I average my bases, 7 and 3, that has an average of 5. I multiply by my height, 4. I get an area of 20. Okay, so we already know that when we integrate this function that we should get 27.5. But if we were to do this analytically without the graph, we would need to recognize that our boundary of our piecewise 0 is between our limits -3 and 4. So that really all that means is that we have to rewrite this as the sum of two different integrals. And that's what we just did on the graph. So if I integrate from -3 to 4, f of x, I know that I could think of this as the integral from -3 to 0, because that's the boundary of my piecewise, plus the integral from 0 to 4. All right, so when we go to actually do this, I know from -3 to 0, I'm using the top part of my piecewise. So I would use 1 minus x as the function I'm integrating, and then I'm going to add to that the integral from 0 to 4 of x plus 3. And this is really important. Don't forget your dx when we do this, because the dx kind of closes the integral. And if we forget the first one, that plus sign is going to look like it is part of the first integral. All right, so when we find our antiderivative, let's see, our first one, our antiderivative is going to be x minus 1/2 x squared. And I'm going to integrate that from -3 to 0. And I'm going to add to that, sorry, I'm going off screen a little. I'm going to add to that 1/2 x squared plus 3x evaluated from 0 to 4. All right, so when we do this, we get, let's see, we plug in our 0. So for our first the number that we plug in, we're going to get a 0. When we plug in a, minus f of b minus f of a, when we plug in our -3, we're going to have a -3 minus, let's see, 3 squared over 2, so minus 9 halves. All right, so that's our first evaluation. And then we're going to add to that, I'm going to do brackets to kind of set apart the two things that we're evaluating. So when I plug in a 4, I'm going to get, let's see, 4 squared over 2. So that is 16 over 2, 8. And let's see, plus 3 times 4, so plus 12, minus 0. All right, so when we add this all up, we do indeed get a sum of, there we go. We do indeed get a sum of 27.5 there. So when we integrate absolute value functions, what we need to remember is that an absolute value function is a piecewise defined function. So if I think about the absolute value of of f of x, I know that that's just going to be my function f of x anywhere f of x is greater than or equal to 0. If I think of values that would make f of x negative, I'm just going to think of this as negative f of x. So the negative out front by multiplication would just cause our outputs to be positive. So that's how we write a absolute value function as a piecewise defined function. So if we're going to evaluate the absolute value of a function, which we will sometimes need to do, we need to figure out when our function is positive and when our function is negative. So we can do this by just finding the zeros of the function and then using a number line to test the function for when it is positive or negative. So for our first example, we want to integrate the absolute value of sine of 2x, and we want to evaluate that from 0 to 3 pi over 4. So the first thing we need to figure out is where is the sine of 2x positive and negative. So I'm going to start by setting the sine of 2x equal to 0. And I could take the inverse sine of both sides, but I could also just think about my unit circle. And I know that on my unit circle, that the sine of anything, so if I just think of the sine of like any junk in here, that when I am between 0 and pi, my values are positive, but at 0 and pi, that's where the sine of 2x would be equal to 0. So really, I could express this as pi plus pi n, because every time we move pi radians around the unit circle, which is halfway around the unit circle, we're going to have a sine value of 0. So I could think that this will happen when 2x is equal to pi plus pi n. And actually, just to simple that up, we could just say pi n. I don't really know why I started with pi, because this is the same as saying like 0 plus pi n. So like if I start at 0, this is 0 plus pi times 1. So that would probably just make this a little bit easier. All right, so anytime I input a number, a whole number for, or really an integer for n, I'm going to get a place where the sign of that value is 0. So since this was a 2x and not just an x, I still need to solve this equation for x. So I'm going to divide both sides by 2, and I get that x equals pi halves times n. I'm just making a lot of mistakes this morning. Okay, so anytime I plug in an integer for n, I'm going to find a spot where the sign of 2x is 0. So I'm considering this closed interval from 0 to 3 pi over 4. So I'm just going to start at 0 and go to 3 pi over 4, because those are the limits of my integral. And from 0 to 3 pi over 4, the only time that the only value that I could plug in for n here that will generate a value that's between 3 pi over 4, 0 and 3 pi over 4 is 1. So from 0 to pi halves, my function is going to be 1 sign, and then from pi halves to 3 pi over 4, my function is going to be a different sign. Okay, so if we go ahead and test this, if I pick anything on this interval to plug in here, so like let's say that I plug in pi over 4, the sign of 2 times pi over 4 is going to be positive. So our function is positive from 0 to pi over 2. And then from pi over 2 to 3 pi over 4, and again, I could plug in anything on that interval and test it, but that is where our function sine of 2x is going to be negative. So when I go to evaluate this, what I need to do is I need to break this up I need to break this up into two integrals. So from 0 to pi over 2, since my function's positive there, I don't need to do anything. I'm just going to drop the absolute value symbol because I know that that is where the sign of 2x is positive. But from pi halves to 3 pi over 4, I'm going to get negative values. So I could think about integrating, like adding to this the integral of negative sine of x, or sorry, sine of 2x dx. But what I could also do instead is just pull that negative out and make this subtraction. So it's like I'm subtracting a negative. So we're going to integrate this from pi over 2 to 3 pi over 4. So since it's the sine of 2x and not just x, we really have to consider doing like a little u-sub here, but this is such a simple u-sub, we could probably just hold our thinking in our head about it. So I'm just going to write out that I would let u be 2x, so that means my du would have to be 2 dx. So really, I need to pick up a 2 on the inside, and that means I have a 1/2 on the outside. All right, so I'm not going to actually do the u substitution. We certainly can, but I know, like just mentally, that what I have on the inside now is just the sine of u du. So I know that when I integrate the sine of u du, I'm going to get negative cosine of u. And I'm just going to go ahead and plug back in my 2x, so I should get negative cosine of 2x. So what we have here is 1/2 times the negative cosine of 2x. I'm going to go ahead and put the negative out front. We can do that. So I just have the cosine of 2x here. And we're going to integrate that from 0 to pi over 2. And then out here, I already have the subtraction, so I have a minus 1/2. But again, when I integrate, my antiderivative here is going to be negative cosine of 2x. So instead of having a double negative, I'm just going to write plus the cosine of 2x there. So when we go to evaluate this, I'm going to just keep this negative 1/2 for our first evaluation out front. And we end up plugging in, we get the cosine of 2x, or sorry, of 2 times pi over 2. So that's really just the cosine of pi minus the cosine of 2 times 0, so minus the cosine of 0, plus 1/2 times the cosine of 2 times 3 pi over 4. So that's just the cosine of 3 times pi over 2 minus the cosine of 2 times pi over 2, which is again the cosine of pi. So when I go ahead to clean this up, I have the cosine of pi, which is negative 1 minus the cosine of 0, so minus positive 1, plus 1/2 times the cosine of 3 pi over 2, which is 0, minus the cosine of pi, so minus negative 1. So we end up getting negative 1/2 times negative 2 plus positive 1/2 times 1, which is just positive 1 plus 1/2, or 3/2. So if we wanted to understand, and I'm going to kind of go out to the side here, but if you have room to kind of sketch this in, if I wanted to think about what's happening when I integrate this, if I were to consider the graph of the sine of 2x, so if I'm graphing the sine of 2x, remember the period for that function is going to be pi, so halfway between 0 and pi at pi over 2, that's my 0, so I should be thinking of my sine of 2x curve like this. And what we're integrating, we said, was from 0 to 3 pi over 4, so like right here. So really what's happening is we know that this part of our area, this was the positive 1 that we got when we integrated. So we know that that area is 1. That came from like our first evaluation. But if I didn't take the absolute value of sine of 2x, this area would be a negative 1/2. But when I take the absolute value of a function, it's just going to reflect anything that is below the x-axis to be above the x-axis. So really, our sine curve comes back up again. So the other 1/2 that got added to this would be the area if I reflected the negative part of our graph over the axis to be positive. All right, go ahead and pause the video and see if you could work out this next one. All right, well, I'm going to keep rolling. So we said that the first thing we have to do is figure out when our function is 0, if we're going to evaluate the absolute value of our function. So I need to set this equal to 0, and then factor, and then keep factoring. And I find out that this is going to have zeros at -2, 0, and 2. But the only one I'm really worried about, because I'm looking at my limits of integration here, 2 is the only number that's between 0 and 3. So I'm not really worried about this function having a 0 at -2 or at 0, since that's where I'm starting my evaluation. So from 0 to 3, in considering what's happening at 2, I want to consider the sine of x cubed minus 4x. So if I plugged in, let's say I plug in the number 1, and I'm going to plug that in factored form, I would have 1 times 1 minus 2, which is negative, times 1 plus 2, which is positive. So that's going to make this part of my function negative. So my value there would be negative. If I plug in like a positive number, like 2.5, I'm multiplying a positive times a positive times a positive. So my function is positive there. So it's really just this first part from 0 to 2 that I have to worry about. So again, I'm going to break this up into two integrals. What I want is I want negative x cubed minus 4x. That's what I want to integrate from 0 to 2, because that negative out front will change the sign and it will make that area that was under the axis positive. So instead of putting the negative in my integrand, I'm just going to put it out front. So I have negative the definite integral from 0 to 2 of x cubed minus 4x dx. And I'm going to add to that, since this area is already positive, I don't need a sign change. All right, so when I go to find my antiderivative there, I'm going to keep my negative out front for this first one. So we would get like 1/4 x to the 4th minus 2x squared. And that's what we're going to evaluate from 0 to 2. And then we're going to add to that 1/4 x to the 4th minus 2x squared, evaluated from 2 to 3. All right, so I'm going to keep my negative out front. Let's see, I get 2 to the 4th power divided by 4. So that's like 2 to the 4th divided by 2 to the 2, which is just 2 to the 2. So I get 4 there. Minus 2 cubed, essentially. So minus 8. Oops. And then I'm going to add to that 3 to the 4th divided by 4. So let's see, 3 to the 4th is 2781. So 81/4 minus 3 squared. So 9 times 2, so minus 18. Minus, when I plug my 2 in, we said that we already know that when we plug our 2 in there, we're going to get like a 4 minus 8. So that was the first thing we did. All right, so if we simple this up, this is -1 times -4. So we just get a 4 there. I'm just going to keep this right now as 81/4. This is another another -4, but minus -4. So -18 minus -4 is -18 plus 4. So this becomes minus 14. And if I go ahead and combine that, that's really 81/4 minus 10, which is 81/4 minus 40/4. So our final answer there is 41 fourths.